All right, good afternoon, everybody. My name is Sven Degroote. I'm a machine learning engineer at ML6, and I'm going to walk you through one of our use cases that we have done together with Sporttotal.tv. It's about video analytics for football games. Maybe just a short word about ML6. So we are a Google Cloud partner, and we are a consulting services company specialized in machine learning. So we try to tackle problems together with clients by using machine learning. All right, let's get into it. So first of all, a word about Sporttotal, our customer. So they are an international player in the sports business, and they have been traditionally known for broadcasting big events on television. And they were looking for new business opportunities, mainly in the digital space. So what problem were we trying to solve together with them? I've tried to summarize it in one sentence, and there's quite a lot of words in it, but I will try to walk you through it and analyze it part by part to see what does this mean in terms of system requirements and how can we use Beam to solve this problem, basically. So the question was really, can you, for us, design and create a platform that can handle auto production and broadcasting for up to hundreds of games per weekend with as little time delay as possible. So this is mainly concerning amateur games, not professional football games, which are broadcasted on television right now, but really focusing more on the lower level amateur leagues. So I will walk you through this problem statement to see what does this actually mean in terms of system requirements. So the first part is about auto production. So we need to start from a raw video feed, and we need to actually enrich it, enhance it, so it actually looks like a real video game or a real football game that you are watching on television. So the first part we need to do is we need to enhance the raw video feed. We need to process it. So how can we auto-produce this video feed? The first thing we need to do is we need to have player and ball tracking. We need to have team detection, because if we have this, we can we know where the action on the field is happening, so we can have a right zooming in of the camera to show you the video feed. And this is typically something you would do on a frame-by-frame basis. So, and the result of this would be a minimap, as you can see. So you know where each of the players are, from which teams they are, and where the ball is. So you can also see where the action is going on. So if you have a streaming feed, and this is the timeline, so starting from second 0 to second 4 and so forth, if you would work with a frames per second rate of 10, that means that in the first second you would have 10 frames, and so by every frame you just try to predict where the players and where the ball is. So this is typically something you do on a frame-by-frame basis. The next part we had to solve was also event detection. So anything that involves a referee, just think about goals, fouls, corner kicks, free kicks, and so on. So this is also something we had to detect and predict based on the raw video feed. And this is typically something you do on a sequence of frames. You cannot just detect a foul based on a single frame, or I would say it's very hard to predict that even for humans, let alone that we would try to predict this via machine learning. So just to give you an example, if you have a foul, you really need to see the motion of the players to be able to predict which player made a foul to which player. So it's really about a sequence of frames for event detection. So if we look at the same video timeline again, that would mean that in this case we have a sequence of frames, and technically this means that we will have sliding windows. In this case we will have, for this type of event, as an example, we had sliding windows of 3 seconds every single second. The second part of the problem statement was focused on really infrastructure-wise. So can you broadcast it for up to hundreds of games per weekend with as little time delay as possible? So that means that your infrastructure will need to be highly scalable. And I've just tried to list up here the 3 biggest important factors for our solution. Is that it needs to support streaming feed, of course. It needs to be highly scalable. If you have your game starting at 3 p.m., and then again at 6 p.m., you will have these kind of peak hours at which a lot of games start. So at that point in time, your infrastructure needs to scale a lot to meet these demands, because you have more and more games starting. And also, as I already said, so the auto-producing part involves a lot of machine learning. So we need to have an easy way to interact with our machine learning models to get those predictions. So let's maybe try to summarize a bit and look at the problem landscape. So from left to right, so we have a camera at a football field. It's recording a single frame. It's about 4,000 by 800 pixels. And it's going to upload that video feed onto the cloud, and that's being made available on a URL where we are able to start from. And then what's being expected is that we basically start from this URL, and we just take in the raw video feed, we process it, and we make it available in a player so people can actually watch it in an enjoyable way. And I'm going back to the problem statements. So I said with as little time delay as possible. I know this is a quite vague problem statement. The order of magnitude was about 10 to 20 seconds. So we had a time span of 10 to 20 seconds. In between, the video gets uploaded, and we need to display to a user who is watching our solution, basically. So it's quite a high demand, I would say. So now I'm going to show you where we started from. So this is the raw input feed that we got, which we need to process. And hopefully this link will work. I will try it. So hold on. You can use this one as well. So this is the start of the feed. So also to mention, these are amateur games. So the feed is starting about 15 to 20 minutes in advance of the start of the game. This is not always exact. So also our machine learning had to handle when the game was starting. So we had no clear point of where we need to start from. So also for a user, just imagine that you would watch this. This is not really enjoyable, right? You don't have any timer. You do not know whether the game has started. How long has it been going on? What is the score? So our goal was really to enhance these raw video feed into something which is actually watchable and kind of looks like a professional game. I'm going to try to fast forward a bit if the internet wants to go along. Okay. No. Okay, what I was trying to, or what I was, okay, it goes again. So you can see that it's quite hard to follow where the action is going, right? Definitely if the ball is at the other side of the field, it's very hard because the camera is placed at a point where it's actually quite flat to look at. So you can see that if you would like to watch this game, this is not really so enjoyable to watch it. So we will come back to this, how we enhance this into something which is watchable and which is enjoyable to look at. Okay. Okay. So how did we build the solution? This is a high-level overview of the architecture that we have built. So I'm going to go from left to right to walk you through the solution. So first of all, we are starting from a streaming feed, which is hosted on a URL. And this is a video file, but our machine learning models do not work with video files. We need to feed them frames. So that's why first we transcode the video. So we go from the MP4 file into separate frames, basically. And we use a frame per second rate of 10 in our use case. Then we publish our frames via PubSub. So PubSub is managed Kafka. And then we use Dataflow to do the heavy lifting. So here we will use Dataflow as our engine to really process the video feed and to really process it and give the output to a database, which is in our case Google Bigtable. We also have Kubernetes engine on this slide. Why is that? Because as I said before, we have a lot of machine learning models which are trying to predict where are the players, was there a goal, and so on. And these models were hosted on Kubernetes engine, and we then interacted from Dataflow to Kubernetes engine to get our predictions from our machine learning models. So once Dataflow has done the processing of the frames, it's going to store the data inside of Bigtable, and then we have a player which is sitting on top of Bigtable to really visualize the processed output. So if we go back to our problem landscape and now turn it into a solution landscape, on the left-hand side we have our transcoder on Kubernetes, which is turning the video feed into frames. The data is being sent over via PubSub. It arrives at our pipeline in Dataflow. Then we are processing the video feed. We are interacting with Kubernetes to get our predictions from our machine learning models. We store the data inside of Bigtable, and then we have a player hosted on Kubernetes engine, which is displaying the information which was stored in Bigtable. So I'm going to zoom in now on the center part of the solution. So we used Kubernetes engine for hosting our ML models, mainly because we had different models, and these models have different specifications in terms of CPU, GPU, and so on. So we use different node pools to host our different machine learning models. And we exposed our models to Dataflow via an internal load balancer. So these are only reachable from within the GCP project, so within your VPC, basically. Then Dataflow is windowing the frames because they come in out of order, and it's doing all the processing, and it's going to scale as it detects higher workloads coming in. So we have more and more games starting. Apache Beam will detect this, and it will scale out to meet the requirements in terms of workload. We chose for Kubernetes engine mainly because we needed GPUs for our machine learning predictions, and within Apache Beam this is not feasible, and also within AI platform and former ML engine this was not feasible at that point in time. So this is our motivation why we went for Kubernetes engine with TF serving. And then we used Beam mainly because, as I told you before, during the problem statement we have sliding windows. So there's a lot of complexity going on with making sure all the frames are in the right window, that they are in order. So this involves a high level of complexity, and our goal was also to get to the solution with a minimal amount of development time. So this is why Dataflow was for us the perfect fit to really go forward at a high pace with developing this solution. All right, so let's have a look at what the output gave us. So I'm going to play this, I think, multiple times to explain it. So this is the original frame that you saw earlier on, but now we have this swarm, which is going to zoom in because we know where the players are, where the action is happening, and you can see that now the pane is actually shifting to where the action is happening. Also, you can see that we enabled bounding boxes. Per team, they have a different color. They might switch around now and then, but this can be solved by further smoothing. Also, on the right top, you saw a minimap. And sometimes it can jump a bit, but this is to be solved with smoothing. I'm going to play it again. Okay. And actually, while we were looking into this solution, we caught ourselves watching the game. So previously, we were like, this is not really enjoyable to watch, but as soon as we had this up and running, we really caught ourselves watching the video for 5 minutes, and we're like, okay, we need to go back at work. So it was really something that we saw ourselves that was really cool to watch it. So I'm going to play another video as well. I'm going to go to the next one. Yes. So I told you before that the game starts about 15 to 20 minutes inside of the stream. But you can imagine that players do not want to look at a warm-up. So ideally you have a solution which, let's say, pings a message to users whenever the game starts. So also we had to come up with a machine learning model which was able to predict the start of game, because at that point in time we could start the clock of the game and we can start keeping track of goals and so forth. So this was also a very important milestone to have a model which is able to predict the start of game. I'm going to also show this a couple of times. So this is the probability chart for probability, and you will see a spike whenever the kick. So it spikes to 98% probability of a start of game, then 82, and then it drops down. So it's a very narrow peak, but it's a very obvious peak. So I'm going to play it again, if it was too fast. So you see it spikes up to 98% probability. So this is how we checked our models on, are they performing well? What is the probability? How big is the peak? Should it be more narrow? Should it be more broad? And this is how we've then visualized the prediction that of all of the information that was processed through Dataflow. Okay, I'm going to... Now I'm going to take a closer look into our Beam pipeline. So we use Dataflow for running Beam. I'm going to go from left to right. So as I said before, the frames come in out of order. So, and we need to do things on every frame, which I told you before, like the player and the ball tracking, this is typically something that you need to do on every frame. So everything we need to do per frame happens on the left-hand side. And then there is more complex logic when you need to combine frames. As I said before, we need to window them, we need to order them, and this is all happening at the right-hand side of the pipeline. So moving from left to right, we are reading our messages from PubSub. They're coming in out of order. In a first step, we will pre-process them because our model is expecting a specific data input, and we need to pre-process it so it matches that specific input format. And what we are passing between the step of pre-process and predict is a tuple with as key the game ID and as value the frame information. So this is the frame itself and also some metadata about the frame. And in this prediction step, we are making the call to Kubernetes to give us the prediction for player and ball tracking and team detection. So anything we would do on a frame-by-frame basis. And then when we move into the right-hand side, I will cover the upper part, so the start of game. So in this case, we used, our model was expecting windows of 3 seconds. So in our case, we need to window the frames into windows of 3 seconds. And that's what's happening in the window into sliding windows. So there we are saying, please window this data into sliding windows of 3 seconds every 1 second. The next step, which is adding the window time to the key, is some kind of thing we had to solve because we had some issues with parallelization, and I will come back to this as well. But what it's basically doing, as you can see, it's adding the window time inside of the key of the tuple. I will come back to this later on. And then the next step is the group by key, and this is where we materialize the windowing. So here we are saying to Beam, please materialize all of the windows, all of the frames within this window, and group them together. And this is what you can see on the data in the next step. So you see the tuple is still the game ID and the window time, but now the value is the list of the frames. And once we have the list of the frames, we can order them and we can send them to our machine learning models. So again, we always have a pre-processing step to make sure that the format is in line with what the machine learning model expects. And then we do our prediction call. So we send our 30 frames, which are in order, to our machine learning model on Kubernetes engine. And this is repeated several times for other type of events. So start of game is using 3-second sliding windows, but a goal could use sliding windows of 5 seconds, even 10 seconds. So every different feature that we wanted to have in the solution does have different specifications in terms of sizes that it expects. So this is why also Beam really allows us to manage this complexity with as little development time needed, because it's just all out of the box with the windowing functionality. Now I'm going to cover some of the difficulties that we faced, but I'm sure with this audience it will be pretty obvious. So one of the things we came across was that windowing with streaming data is hard. I think everybody who has done this before can confirm this. But in our case, luckily we knew exactly how many elements we were expecting inside of a window, because we were working with 10 FPS, 10 frames per second. If you have a window of 3 seconds, that means you need to expect 30 frames. So you know that you need to have this amount of elements in your window, and then you can easily use the triggers within Beam to say, okay, once you have seen 30 elements, just fire the window. So you do not need to wait for the watermark. The other thing which I mentioned before, where we added the window time to the key, was because I'm going to first explain what happens if you don't do this. If you don't do this, all of your elements for a given game, all of the windows, they will have the same game ID inside of the key of the tuple. And what happens then is that all of the windows for that game end up on the same worker, on the same node. And this is not something that you want in our case, because we wanted actually to parallelize this step. So what we saw that the latency was picking up quite high, and we noticed that all of the elements, all of the windows were processed on the same worker. And this is why we had to look for a solution to solve this. And it's an obvious rule, so it's on the slide as well. So the key is really the unit of parallelism, so you really need to watch your keys. And this is why we added the window time inside of the key of the tuple, and then it's indeed parallelized across multiple workers. Next to the beam difficulties, we also had some data difficulties, as you can see. So this is the data that we had to train on. This is more on the machine learning part and data part, I would say. But it's funny to look at because, yeah, if you look at the data that we had, you have fields with a lot of shadow. You have even ice hockey fields, which were, I think, not correct. But you see that you need to be very aware of what data you're putting inside of your pipeline, because rubbish in is rubbish out. So also here we had to look out for what data we're really putting into our pipeline. Another difficulty which I didn't mention yet is that if you look at the frame that we get in, there are no straight borderlines of the football field. It's a fisheye lens. So if you want to have normalized bounding boxes, if you really want to know the XY coordinates inside of the football field, you will need to do a transformation. And this is why if you go from the top image to the middle image, we actually to dewarp the image. So we get straight borderlines, and then we can do the transformation into X, Y coordinates, as you can see on the lower image. And this is another video which is showing you more the trailing. So also when you have the team detection in place, you can start trailing players, individual players, and you can try to create statistics on the distance covered per team, the ball possession, and so on. So this is just a bit to visualize how you can follow a specific player. You can see that sometimes the trail drops, but again, with a bit of better smoothing, this should be solved. Also, you can see that it's hard to do it on the other side of the field, again, because the hardware was fixed for us. So we only had one camera at one side of the field, and we had to work with that. So you can imagine that if you have 2 cameras, or even 4 cameras, this could be enhanced quite a lot. Just gonna check, okay. Just to end up with some figures this session. So I've mentioned before, so we had 10 frames per second, and this is for a single game, these numbers. We stream about 150 minutes, so that means we have about 90,000 frames going into the pipeline. Each frame is estimated about 750 kilobytes. So if we look at the total amount of frames we are processing through our pipeline, we end up with about a small 200 gigabytes of data, and this is just for the start of game event. So the upper part, which I told you before, but just imagine if you have multiple events in one pipeline for a single game, like yellow cards, red cards, goals, free kicks, you easily get up to a terabyte. If you have hundreds of games per weekend, you can do the math yourself, but it gets quite big quite easily. So this is just to give you some feeling with the amount of data that we worked. I hope you enjoyed this session. Thank you for your attention, and I will be gladly to ask you to answer to your questions.
Thank you so much for this talk. Any questions, anyone? Over there. Okay.
Hi, great talk and nice things you've done there. Just a question about the data that you used for training the models. Where did you get? Did you label it yourselves, and how long did it take, and how many people?
That's often the first question I get when talking about this. We received annotated data in the beginning, so we anticipated this and we got annotated data. However, it was not in line with the expectations that we needed to really get high accuracies. So what we've tried to do is we get some ground truth data. We train a first version of our model, which is able to predict new outcomes. And then we use those predictions to get faster labeling. Because you know where to look, you know where the interesting parts of the video are. So you use this kind of prediction data points to use by your annotators to have a higher pace of annotating, because otherwise you need to watch the 90 minutes to really see where the goal is happening. If you have a machine learning model, which is not perfectly, but it does quite get in the area of getting a prediction quite right, then you can label more effectively. So this is all, it was really an iteration cycle.
Thanks, really nice talk. How do you do with kind of these events, like start of game, that only kind of happens once? do you kind of shut that part of the pipeline down, or you keep making predictions for that?
Yes, so indeed, so very good question. So obviously, you cannot just rely on the probabilities per frame. You also need to have some post-processing on what logic can happen for a football game. You can never have a double start of game event, so there needs to be a post-processing component which is looking over what you are acknowledging towards the player. So this is something which I've hidden from this presentation, but is in place after you pass the information to your player. So there is business logic afterwards.
Thank you. Any other questions? There you go.
So another one as well. What is the price per game for running this? Is it worth it?
So when we got this question or this problem statement, the first goal and priority was to make it work, and then secondly, to make it cheaper. So this is why we didn't, in the beginning, we just were really focused on development time. And if you look at this, it runs for a full game, and it will come close to about 70 to 80 euros. But we did a rough analysis on how much we can reduce it, and we think we can get it below 10 euros. But of course, this is order of magnitudes we're speaking about, so don't take this as ground truth. This is just a feeling that we had.
All right, anyone else would like to ask a question?
Did you also experiment with other runners? Did you compare other runners?
Sorry?
Did you compare other runners like Flink or Spark or?
It's a, yeah, in our case, so I've mentioned maybe some background. So as ML6, we are a Google Cloud partner, and we mainly worked in the past also with Dataflow. So in our case, we just went for the solutions which we know. So we also used Python SDK. So we really went for the tools in our luggage which we already know, let's say. So we did not think about other runners at that point in time. Maybe if we move forward by making it more cost efficiently, we need to, let's say, take a step back and really look at the architecture. But this is just to get an MVP working.
Okay, we have another question.
Thank you for talk. How it will be difficult to use the same approach for other games?
It's very hard to understand the question from here because the sound is not really...
How it will be difficult to replicate the same approach for other type of games?
I'm going to repeat the question. So is it difficult to repeat this kind of solution for other type of games, like other sports?
Games, like hockey, basketball, yes.
Other sports, yes. Then. Good question. We designed this solution to, let's say, reuse it for other sports as well, because that was also the direction we got from Sporttotal.tv. So we also need to make it scalable towards other sports. So we have, I think, in general, if you look at the Beam structure, the Beam pipeline, it's quite modular. So you can plug in other events as well. It's just about training other machine learning models based on new data. But the pipeline structure itself, the orchestration and the infrastructure should be quite similarly for other sports.
Okay, we have time for one last question. Okay, thank you so much for this presentation, and we'll resume in 20 minutes. Enjoy your coffee break. Thank you.